Ben Barletter. I'm going to be talking about the bomb calorimeter experiment. So here we go. The introduction. This experiment is designed to measure the heat release by the combustion in this oxygen bomb we're going to have in the lab. The oxygen bomb calorimeter is kind of a standard for accurate measurements of different heats of combustion for different fuels that you might not know the heat of combustion for, and maybe you want to test how much it is. So it's in widespread use today in chemistry labs and I guess mechanical labs. So the objectives: become familiar with the procedures and analysis techniques associated with the oxygen bomb calorimeter, and we are going to measure the heat release by the combustion of the samples provided. One is going to be known, benzoic acid, and we're going to find thermal capacitance of the system from that known heat release. And then we're going to have an unknown fuel sample, and we're going to actually measure the combustion for that unknown fuel sample now that we have the heat of combustion. So the theory: upon igniting the bomb, heat is transferred from the bomb itself to a surrounding water environment, and by measuring the rise in water temperature, we can determine the amount of heat released by the combustion while using that equation right there. Q equals mc delta T. Q is the heat, mc is thermal capacitance of the system, delta T is the change in temperature of the water. So, like I said before, we can burn a known fuel sample. We know Q. We can measure delta T, so we can get mc, and that's the thermal capacitance of the system. Now we can find an unknown Q. Now we have our thermal capacitance, and we just measured the change in temperature again. Also, we have to account for the heat released by the ignition wires. So that Q right there is actually two separate Qs, which is the Q burned by the fuel and the Q burned by the actual ignition wire. So we have to take that into account. So this is kind of a view of the setup of the experiment. We have an igniter, a stainless steel bomb, right there. We have a laptop connected to it, analog digital converter. Here's the water bucket right there, filled with water. Thermocouple right there, stir motor to distribute the temperature evenly so we get a good temperature reading. And here's like a close-up of the bomb. You have the electrodes, you have the crucible with the fuel on it right there, the housing, some check valve, lock lids, stuff like that. So there are three distinct stages that we have to basically prepare. We have the bomb preparation, measure, cut the ignition wire, place the fuel into the crucible, connect everything, add water into the bucket, or the bottom of the bomb, close the lid on the bomb, screw the locking kid, pressurize, depressurize the bomb, alternating it, and that'll get all the air out. You can pressurize it to 30 atmospheres. Then the water jacket itself is just a bucket, pretty much. You fill it up with 2 kilograms of water, place that into the actual calorimeter. The instrumentation, you start up all the data, make sure it's working right, then get it ready for writing data. Put the bomb into the bucket of water, connect all your wires, electrical leads, check the ignition circuit, check it for continuity, make sure it's a nice closed circuit. Make sure the stir thermocouple isn't attached to anything like the bomb or the bottom or whatever. Turn on the stir, start recording the data, ignite the fuel. That's probably the fun part. Then continue to take data until equilibrium's reached, stop logging data, save it, then repeat everything for an unknown fuel, because before all this was done with a known fuel. Shut down, turn off the stir, remove the lid, disconnect the bomb, depressurize it, open it, measure the length of unburned ignition wire, compare that, to get the energy output by the ignition wire, clean everything up. So I did some expected results, 2 kilograms of water, 3 kilograms stainless steel. The thermal capacitance of the system, I got a value there about 10 kilojoules per Kelvin. I found the expected Q released by the benzoic acid, and that turned out to be like 27. So then I used that first equation that we had before to find C delta T, which was expected to be about 3 degrees Kelvin, or same as 3 degrees Celsius change. Source of error, I mean, basic humans, data, instruments, error, I mean, using different data tables and whatnot. All these errors propagate through. And practical use, you can measure different unknown fuel combustion heats, and those are my references.